podcast is brought to you by LMU Munich.
Okay, thanks. I'm going to talk about applications of holography or ADS-CFT correspondence to quantum field theories at strong couplings, concentrating on finite temperature applications. So here is the outline of my talks, or at least what I hoped to talk about in these 3 lectures. Today I'm going to give you some introductions to the subject and talk about hydrodynamics as a theory describing long-distance physics of finite temperature mediums. Next, in the next lecture, I will describe how you can use ADS-CFT correspondence holography to compute quantities like the kinetic coefficients of like viscosity of strongly coupled media. And the third lecture, if I have time, I will talk about slightly different topics, namely a possible application of holography in non-relativistic physics, namely the physics that might be relevant for strongly coupled fermions, and I will describe the system. So I hope that you have heard from Johanna Ermenger last week that we have now a very interesting tool that allows us to understand a class of strongly coupled quantum field theory. So the method is called holography or ADS-CFT correspondence. And the name ADS-CFT comes from the 2 sides of this correspondence. You have the correspondence between a theory without gravity on one side. In the simplest example of holography, that theory is the n equal 4 super Young-Mills theory. But there are other theories that can be put into correspondence with theory of gravity. So some theory with gravity. In a higher dimension. So in the case of n equal 4 super Young-Mills theory, the theory with gravity that on this side is the type 2b string theory in ADS5 cross S5 background. This is a string theory in 10 dimensions. The interesting part of this geometry for our purpose will be this ADS5, the 5-dimensional part. And you notice that there is one extra dimension compared to the number of space-time dimension in an n equal 4 super Young-Mills theory that lives in 4 dimensions. Okay. This correspondence is very non-trivial. As you see, it's the correspondence between 2 theories living in different dimensions. The metric, let me write down the metric for ADS5 cross S5. ds squared is equal to r squared minus dt squared plus dx squared plus r squared over r squared dr squared. So this is the part of the metric that is anti de Sitter in 5 dimensions, and there is also the 5-dimensional sphere with constant radius. We are going to use this correspondence to extract information about theories without gravity from the theory with gravity. And why it is useful? It is because there is the following correspondence between the regimes in the two theories. So let me recall that n equal 4 super Young-Mills theory is a gauge theory, and as a gauge theory it has the number of color. The parameters of these theories are the number of color and C. In the real world, in QCD, the number of color is 3, but in this in a more general theories, we can have arbitrary number of colors. And another parameter is the coupling constant, the gauge coupling G, which can be combined with NC to the so-called 't-Hooft coupling, lambda equal G squared times NC, the number of color. And the importance of the 't-Hooft coupling is that it is the parameter that govern the perturbation theory. If you draw Feynman diagrams and then compute order by order the Feynman diagram, you see the in the large NC limit, the Feynman the expansion is an expansion is a Taylor series over this constant lambda. So the gauge theory has two parameters, 1 and 2. How about the on the other side, the string theories have, as you know, it has is characterized by the string coupling, and the string scale that is related to the usual alpha prime as square root of alpha prime. In this metric, we also have another length scale that is the curvature of the space-time, the curvature of ADS space or the curvature of the sphere. So there is an R. So there are three parameters, but actually there are only two dimensionless parameters because both the string scale and the radius are dimension-full parameters from which you can construct one ratio, dimensionless ratio, the curvature scale in unit of the string length. The utility of the ADS-CFT correspondence for quantum field theories come from the particular formula that relate the 't-Hooft coupling with the ratios of these two length scale. So lambda is equal to the ratio of these two length scale to the fourth power. Okay. If the 't-Hooft coupling goes to infinity, if the 't-Hooft coupling is very large, then the corresponding limit of the theory with gravity is the limit when the curvature of space is very large compared to the length scale. And in this limit, the string theory becomes simple. It becomes just a theory of gravity. So we have this mapping between a quantum field theory in a very difficult limit, the limit of very large coupling constant, where the usual expansion according to Feynman doesn't work. This limit mapped onto an easy limit of string theory, namely it's mapped into Einstein gravity. Okay. There is another simplification so the 't-Hooft, when you take the limit of large NC, that limit map into the classical limit. So in combination, if you are interested in quantities of quantum field theories in the doubles limit of large large number of color and large of coupling, then you are talking about Einstein gravity in the classical limit, and that is something that everybody can solve. So we have heard from today's lecture by Atish that black holes in theories with gravities, we typically have black holes, and we know that these black holes can be characterized by a finite number of parameters, for example, by its mass or by its charge, or if you have more charge, by its mass and the finite number of charges. We understand that black holes are thermodynamic systems that can be described as any thermodynamic system. It can be described by the temperature and, say, chemical potential. So as in a thermodynamic system, for example, if you take a gas of air in a box, you can describe this gas by, say, the total energy and the total particle number. Alternatively, if this volume is big, you can talk about the temperature and the chemical potential and the volume. Now, combining this with ADS-CFT correspondence, we can say that the black hole, if we have a black hole, so I'm drawing the diagrams not very well because the left-hand side here corresponds to the right-hand side on this picture. If we have a black hole in the theory of gravity, for example, if you have a black hole in this ADS5 cross S5, it actually should correspond to some thermal object in quantum field theory. Say, if we generalize that metric that I have written down there to a metric with horizon. So let me write it down here. Plus r square over r square f of r dr square, okay, and then f of r is equal 1 minus r naught to the 4th over r to the 4th. One can actually check that this is a solution to the Einstein equations, r mu nu minus a half r g mu nu equal some constant time g mu nu, where this constant is related to the cosmological constant. This metric should correspond to some thermal state of the quantum field theory. The logic here is the following. We know that there is a correspondence between the quantum field theory and theory with gravity, and we know that in the theory of gravity we have some object that carries a finite temperature, and it's natural to put that into a correspondence with the quantum field theory at finite temperature. Any questions? So what is this thermal state of the quantum field theory? First of all, if you look at this metric that I have written down here, you see that it has the same structure as the Schwarzschild metric. there is a factor that multiplies the dt square, and that factor goes to 0, like in the Schwarzschild metric that you have seen today. Let's see. Let's move it up a little bit. But there is a difference between this metric and the metric of the Schwarzschild black hole. There is the x square in this metric, which means that the space-time that I'm considering here is translationally invariant. Translationally invariant with respect to 3 spatial coordinates, x1, x2, x3 here. Okay. So if you think about this as an object in 10-dimensional space, one can think about that as a black hole that is curved in space, in like 7 space-time dimension, but it is flat in 3 spatial dimension. So let me call this object a black brane. A brane because it is it has flat three flat directions. Okay. I'm sorry. So it has another r square, d omega 5 square. Okay. So if you think about this as the space-time in 10 dimension, then it is a solution to the Einstein equation where the stress energy tensor is coming from a 5 form. So it is it should correspond to a state of the quantum field theory that is translationally invariant in 3 dimensions, and it has a finite temperature. Basically, it is the state where the whole space is filled with a plasma with a finite temperature. So this is nothing but some kind of a plasma with temperature T. So the whole space is filled with matter with the same temperature T. Okay. Question so far? So in one of the problem in the tutorial you will have is to find the temperature of this black hole. Find the temperature of this configuration, and this Hawking temperature is put into correspondence, is exactly equal to the temperature of the plasma of the quantum field theory to which it corresponds. Sorry? So here I'm talking about the particular case of a solution that corresponds to quantum field theory in 4 dimensions. So this is ADS 5. This part of the matrix is a black hole with the asymptotics of ADS 5, and it corresponds to a quantum field theory in 4 dimensions, namely this n equal 4 super-Yang-Mills theory at large top coupling, large NC, at finite temperature T. So here you see the thing here is that I consider a black hole that fills the whole space. So it is translationally invariant. So there is no place where I can put another black hole. If I want to put another black hole, it has to be local. If I want several black holes, I have to have black holes that are localized in these 3 dimensions. It is an interesting problem what they correspond to, but I'm here for simplicity. I consider just one black hole that fills the whole space, translationally invariant in 3 dimensions. Okay.
Why this means is 1 to the lossy? I mean, why
So the zero temperature ADS-CFT correspondence has been checked, and there are many non-trivial checks, and we understand we have reason to believe that it is a true statement, that the two theory are equivalent to each other. Now, the extension of this to finite temperature is an extra step that we take. I don't know what, at least there is so you can take the following point of view. Let's just take the quantum field theory in Euclidean space and then compactify the one dimension. Then you will see that you have the path integral give you the partition function of the thermal field theory. What it corresponds to is in the gravitational side, you should think about a solution that has this periodicity in one dimension. And this is one of the solutions that has the periodicity, and it has the lowest free energy. So it should correspond to the thermal ensemble. Okay, so there is, at least this is one of the arguments that support identification of this black hole with the thermal ensemble. Okay, and there are various aspects of black hole physics that I will be talking about later. That is exactly the same as in the thermal field theory. So it's also, they are also, what I will be talking can be also thought about as additional checks of this correspondence. Okay, so let's move on. People have used this correspondence to study the thermodynamics of the strongly coupled N=4 super Yang-Mills theory. And what you find is that you can compute the entropy of this thermal plasma. The way you compute the entropy is to look at the area of the horizon on the gravitational side and then identify the entropy of the black hole with the entropy of the plasma. And one of the very early results that people found is that the entropy of the N=4 super Yang-Mills theory in the limit of the large Stokes coupling is equal to 3/4 of the entropy of the same plasma at zero coupling, so at the same temperature. Okay. And both are proportional to the number of degrees of freedom, that is NC to the NC to the second power times the temperature to the third power. The fact that it's temperature to the third power from the point of view of N=4 super Yang-Mills theory come from scale invariance or conformal invariance of the field theory. And as one part of the an exercise that you will I will ask you to do this afternoon is to reproduce this T to T cube from a gravitational calculation. So another thing that one noticed is that the effect of interaction is to reduce the entropy by 25%. Okay? So that can be obtained only from gravitational calculation. We don't know how to compute the entropy of N=4 super Yang-Mills theory at infinite coupling or at finite coupling using quantum field theoretical methods alone.
Strong coupled case and weakly coupled case, because
You it need not be. It well, you can change the coupling, the tube coupling in n equal 4 super Young-Mills theory. That is something that you can change by hand. It need not be any phase transition in between, in the sense that this entropy can smoothly change from the value at zero coupling, the Stefan Boltzmann, just as free gas result and 3/4 of the free gas result without having any singularity in between. So in principle, that is possible, and most people think that it is the case, although no one can prove that. Okay, so so far we have talked about just using black hole physics to understand the thermodynamics of plasma. G goes to 0, yeah, and C fixed and large. Yeah, so here I'm always talk about the limit of large number of colors, and then I change G. G, the coupling constant need to be much smaller than 1 all the time, so that G is always much less than 1, and goes the small top coupling limit correspond to G goes to 0.
In the strong coupling limit, can this entropy be calculated in the quantum field theory or not?
No. In the weak coupling limit, you can compute it. But in the strong coupling limit, you don't have a good tool, except for holography, to compute that. In the regime where the coupling constant lambda is of order 1, you don't know how to compute it. We don't know how to compute it. Okay, so I'm going to talk now about basically what I'm going to talk about is an extension of this correspondence between black hole and black hole thermodynamics and the thermodynamics of plasma to a slightly non-equilibrium situation. So far we have been talking about the situation where everything is in equilibrium. That means that we have the plasma that fills the whole space, and you imagine that the temperature in all places are equal to each other. You can ask the question, what happens if I make the system non-equilibrium? We know that a non-equilibrium system, if we leave it alone, it will reach equilibrium by the interaction between the degrees of freedom. In the gravitational side, we have also we have the similar picture that if we have some configuration where we imagine that the horizon of the black hole changes from one place to the other, then it will relax. The temperature of the black hole changes from one point of the horizon to the other. It will relax to equilibrium. The regime that is very interesting is the hydrodynamic regime. Okay, one can think about this hydrodynamic regime as a regime where the deviation from thermal equilibrium is minimal. It's very slight deviation from equilibrium. So let me draw a symbolic picture of that. Let's imagine that we have a plasma with the temperature as a function of some coordinate x. Well, in principle, there are 3 coordinates. Let me draw only a 2-dimensional picture. And this variation of temperature is very smooth. as a function of x. Now, in order to define what is smooth, I have to talk about the typical length scale of the problem. We have a conformal field theory that doesn't have any intrinsic length scale. If we put that at finite temperature, we introduce the length scale in the problem. That is the inverse temperature is the typical length scale. And it's also a typical time scale. Okay, if we think about 1 over t as a time scale, that corresponds to a typical relaxation time. If we have a deviation from thermal equilibrium, typically everything will be washed out over a time that is proportional to 1 over the temperature. Now suppose we make a configuration where the temperature changes from space one point to another, but it changes over a length scale that is much bigger than 1 over t. Okay. This is the regime where the effective description of the dynamics is hydrodynamics. So let me explain to you why hydrodynamics, what is hydrodynamics and why it is the effective description here. Imagine that you have this deviation from equilibrium. You can ask the following question: can it relax completely to equilibrium over a time that is proportional to 1 over t? Okay, so I told you that we have a strongly coupled system, so the degrees of freedom interact very quickly, and they can establish thermal equilibrium very quickly. On the other hand, here you cannot. The system can, the equilibrium configuration is when the temperature is constant. Okay, so in order for the system to reach equilibrium, you have to transfer energy from one place to the other, and they are separated by an amount that is proportional to the typical length scale that is much bigger than 1 over t. So the time for the system to establish the real equilibrium cannot be smaller than the time that light can travel from this place to this place. So the time for thermal equilibrium to be established diverges when the length scale L here goes to infinity. So here we have the situation where there is a separation between length scale and time scale. Over a time of order 1 over t, so during time of order 1 over t, what happened is that the system established itself in local thermal equilibrium. So local thermal equilibrium means that it is sensible to talk about a temperature and a chemical potential, but the temperature has to be understood as a function of space and time. So if we concentrate our attention on a very small region of space, approximately in this region, we have a thermal state with characterized by a temperature, and if there are conserved charges, then there are also chemical potential. But it takes much longer time for the system to establish true equilibrium. So during time t that can be bigger, with at least of the order of magnitude of the length scale of the perturbations, the system reaches complete thermal equilibrium, global. question so far?
So there was this theorem that any stationary black hole cannot have K should be constant throughout the whole.
K, yeah.
Surface gravity.
Yeah.
So temperature should be constant.
If the configuration is time independent.
Yes.
Yeah. So if you wait long enough so that everything becomes time independent, then the temperature should be constant everywhere. It's the same. So we have seen. So this is the. So you can see the correspondence between the gravitational picture and the quantum field theory picture here. That in quantum field theory, if we manage to create a situation where temperature changes as a function of space, we wait a long time, then the whole system will reach its thermal equilibrium, just the process of equilibration. The question here is how fast this process takes place. Okay. There is a distinction between the black branes situation that we are talking here and say the situation with the black hole, like the Schwarzschild black hole. Here in this black brane case, the space-time has flat direction. So in principle, we can imagine the out of equilibrium configurations where temperature changes very smoothly as we change this radial direction. Okay, not radial, the transverse direction. If you move along the x direction, the temperature can change very slowly. In the case of the Schwarzschild black hole, the horizon is finite, so there is no strict regimes where the temperature can be a smooth function, a very slowly varying function of the position on the horizon. So here we are using the flat direction of the black branes to reach the separation between the two length scale, two time scale. Okay. So as we discuss here, there are two separate notions of thermal equilibrium. The first notion is the notion of local thermal equilibrium that establishes itself during a time typically of order 1/t. And then during a much longer time, the system will reach for long wavelength perturbation. During a much longer time, the system will reach global thermal equilibrium. This black brane, this ADS Schwarzschild large black hole in ADS, it should be large. In large, so that you can have variation over length scales much bigger than the inverse temperature. Okay, for a small Schwarzschild black hole, the situation is the same as in the Schwarzschild black hole in flat space. Okay, so let us draw little diagrams here on the validity of different theories. So suppose we have here, I draw a time scale. Is 0, is 1/t, and here's 1/t. Here's the typical length scale of the perturbations. So here I need the process of thermalization of reaching local thermal equilibrium is a very complicated process. We need the full microscopic theory to describe that. This is the microscopic dynamics that govern the behavior of the system over very short length scale. During this time scale, the system is described by the hydrodynamic theory. And if we wait long enough, of course, it will reach thermodynamic regime of complete thermal equilibrium. So one can think about the hydrodynamics as a slight extension of thermodynamics into the direction of non-equilibrium physics, but the non-equilibrium here is just slightly non-equilibrium deviation, meaning that we still describe the system in terms of thermodynamic variables, but they are function of space and time. Okay, so that's the notion of hydrodynamics.
So you mean for the shorter black hole, because we have no such a two separate scale.
Uh-huh.
So what we have just four macroscopic dynamics or thermodynamics. We have no hydrodynamics.
Yeah.
Shorter black hole.
Mm-hmm. So if we have a black hole whose size is of order 1 over t, and we perturb this black hole so that it goes out of equilibrium, then you will see that it relaxes to equilibrium during a time of order 1 over t, yes. And then nothing, and then there is complete thermal equilibrium. Okay. If you look at, for example, in more technical term, if you look at the quasi-normal mode of this black hole, the imaginary part of all modes is of order of temperature, while in this Schwarzschild the ideal Schwarzschild black hole with the large black hole case, there are a finite number of modes whose imaginary part can be very small.
So, what is the relation between L and main frequency of the system?
Between what?
L.
N? This L? This L is the parameter that we can control. Basically, we perturb the system with the perturbation with the length scale equal to L, and then watch this perturbation to relax.
L is related to main frequency of the system.
It has to be much bigger than the mean free path.
Much bigger than
Yeah, so the hydrodynamic limit is valid at length scale much bigger than the mean free path. And it's, in principle, it can go out to infinite length scale. Okay. So from the point of view of quantum field theory, what happened is that if we perturb this, if you have some perturbation out of equilibrium, these degrees of freedom will interact over a time that is proportional to the mean free path. Right? The one particular particle will collide several times, and then the system will reach equilibrium in a small, at least in this locally, and we reach thermal equilibrium. But it takes much longer time, so that the temperature here, the system here knows about the temperature that has been established here. So the hydrodynamic theory is the regime that we want to investigate both, from the quantum field theory point of view and from the gravitational point of view.
Is it true if we have the large viscosity, these two scales should be closer to each other? Because we have more dissipation of energy. So the relaxation, the global relaxation would be, the time of it would be almost the same as radical order.
So let's talk about these n equal 4 super Young-Mills again. So in n equal 4, or in general a quantum field theory with the coupling constant lambda, if you have the coupling constant that is very small, then the mean free path is not 1 over t, but 1 over t, and there is say a lambda square in front. Okay, and there is a log of 1 over lambda, log of 1 over lambda here. Hydrodynamics is valid when the length scale of the perturbation is much bigger than the mean free path. At any fixed value of the coupling, there is always the regime of validity of hydrodynamic theory. So take, for example, air. The mean free path can be large, but if you go to even larger length scale, you can still describe this air as the hydrodynamic system. The hydrodynamic theory doesn't work for free field theories. If we have no interaction, then there is no hydrodynamics. Okay, so let me now go into the review of hydrodynamic theory.
Is it possible to calculate the time which it taken to reach the equilibrium?
So that's what I'm going to do. So, the quantum field theories that have gravitational duals are usually very complicated from the quantum field theory point of view. For example, this n equal 4 super Young-Mills theory, we have no other tools than holography to compute, say, this finite temperature entropy. On the other hand, the existence of this intermediate theory, the hydrodynamics, tell us that we can do calculations. Hydrodynamics is a universal theory. That means it doesn't depend very much on the structure of the microscopic theory. If you look at a particular fluid, you can describe its time evolution by the Navier-Stokes equation without knowing what kind of molecules it consists of. So we can use the hydrodynamics to check the ADS-CFT correspondence, or else we can use ADS-CFT correspondence to extract the information about the hydrodynamic behavior of quantum field theory. So in the second lecture, I will use ADS-CFT correspondence to compute the viscosity of strongly interacting n equal 4 super Young-Mills theory. Here I will describe how to construct the hydrodynamic theory. So hydrodynamics So if you want to learn more about the subject, probably Landau and Lifshitz is the best place to learn it. It's volume 6 of the course. Okay, so before writing down the equation, we have to settle on the question, what are the degrees of freedom that we have to take into account? So we know that if we have temperature that changes as a function of space, then it is a thermodynamic variable, because temperature can be thought as the energy density if the system and the energy is conserved. So in order to establish thermal equilibrium, you have to transfer energy from one place to the other, and that process takes a time that is at least proportional to the length scale of the perturbation. So temperature, chemical potential are the thermodynamic variables. Chemical potential are related to the, can be thought of equivalently as the density of charges. And if you have a lump of charge, it can dissipate, but it cannot dissipate over a time that is much smaller than the size of the lump. We can have Goldstone bosons. So if you have broken global symmetries, then at 0 temperature we have Goldstone bosons. We know that Goldstone boson has 0 mass if the symmetry is exact, so the dynamics of this Goldstone boson can be arbitrarily slow. The Goldstone boson, if you have broken symmetry at finite temperature, that would lead to the appearance of Goldstone boson in the hydrodynamic equations. Example of that is the superfluid hydrodynamics. for example, helium-4 in the superfluid state is described by a different set of equations than the Navier-Stokes equation, and that leads to a completely different hydrodynamic behavior of superfluid. Another possible set of variables comes if we have unbroken U1 symmetry, unbroken U1 gauge symmetry, that with in the vacuum we will talk about massless photons. If there is an unbroken U1 gauge symmetry at finite temperature, the hydrodynamic theory is called magnetohydrodynamics, MHD. For example, if you want to describe the behavior of magnetic field inside the Earth, you would use a theory that is called magnetohydrodynamics. And there is an extra degrees of freedom there, basically the magnetic field. You have to write down the equation that describes both the motion of the fluid, the variation of the temperature, and also the magnetic fields. And the magnetic fields come from this unbroken U1 symmetry.
We also have some bows on the two-dimensional finite temperature QFTs.
Two-dimension, I will not be talking about two, you mean two spatial dimension or two? Two space-time dimension. In two space-time dimension, typically the hydrodynamics becomes a subtle concept. For example, for conformal field theories, there is no hydrodynamic limit at finite temperature. So here, for simplicity, I will be talking about dimension that is bigger than 1 plus 1. 2 plus 1 and higher, and in particular I will be talking about 3 plus 1 dimensions where things are much more normal. In this talk, I will be concentrated on the examples where there is no Goldstone bosons and there is no unbroken U1 symmetry. So the only degrees of freedom that enters the hydrodynamic description is the conserved energy density that can be parameterized by the temperature and the chemical potential. Okay. The simplest case is when there is no conserved charge except for the energy density. Then everything is minimal. So consider a neutral plasma. The only equation that we have to write down is the conservation of energy momentum tensor. Okay, T mu nu equals 0. So in flat space, that derivative becomes just the usual derivative. Here I'm writing the covariant derivative in case one needs to generalize the equation to curved space. There are more equations here than there are more parameters. There are more variables here than equations. There are 10 independent components of this symmetric tensor. There are force equations, but we know that there is a condition of local thermal equilibrium. That means that this T mu nu has to be expressible in terms of a finite number of local variables of some local variables characterizing local thermal equilibrium. So these are temperature, which can be a function of space. And also, if we take the fluid, it can also move with some velocity. You can have the velocity of the fluid. It can be a function of local velocity. Basically, the temperature, one can think about the temperature as the density of energy and the velocity as the density of momentum. Since energy momentum is conserved, there are four variables. U mu is equal -1. So probably everybody have seen this formula for the stress energy tensor of an ideal fluid. Let us write it down. T mu nu is equal epsilon plus P times U mu nu plus P G mu nu. Written this way, it is just, one can think about that as the boosted form. If we take the this tensor, this T mu nu equal epsilon P P P, and then do a boost so that there is a velocity U mu, then we find this this expression. This is this T mu nu, this epsilon P P P form is valid when U mu is equal to 1, 0. The fluid is at rest. Okay. However, this is only, one can think about that as the zeroth approximation of an expansion. Remember that the that the hydrodynamic theory is a theory that describes very low, very long wavelength perturbation. So one can think about that as some kind of effective field theory. And effective field theories are organized in terms of expansion over the momentum scale or the inverse length scale. So one can add, if one think about the hydrodynamics this way, then one expects that these two terms are the first term of expansion over derivatives. There are next corrections that are proportional to derivative with respect to space and time. Okay. So this part corresponds to ideal hydrodynamics. And this extra part corresponds to deviation from ideal hydrodynamics. Let's talk about this a little bit more. So, any questions so far? So in ideal hydrodynamics, we have d mu T mu nu equals 0, and T mu nu is equal epsilon plus P U mu U nu plus P G mu nu. And this epsilon and P are both function of temperature. Basically, they are defined by the equation of state of the system. And let me recall how if one knows, for example, pressure as a function of temperature, then one can find the entropy density by differentiating pressure with respect to temperature, and then we can find the energy density by doing the Legendre transform. So basically, there is only epsilon and p are not independent. They are all function of one variable. So there are only four independent variables, and there are four equations that four first order equations that govern the time evolution. From this, it is rather straightforward. It's easy to do the following exercise. If you multiply this equation by u nu, and then do some manipulation, we find that the entropy of the system is conserved. Okay, there is an entropy current that is conserved. So that's why these equations correspond to ideal hydrodynamics. In ideal hydrodynamics, there is no dissipation. To the zeroth order of this effective field theory, there is no dissipation. Dissipation comes from the extra contribution to this stress energy tensor. Okay, basically, if you have a fluid that moves with slightly different velocities, if this part of the fluid moves with slightly different velocity than this part, then you will start to see friction between different parts of the fluid, and this friction generates heat, and that leads to dissipation. So in a formal way to see that is to write down all possible terms that is consistent with Lorentz symmetry and contains one derivative. Yeah.
So if there is no dissipation, how come it will means so if it is out of equilibrium, it will not go to equilibrium?
So here, if you stop in this level, then there is no thermalization. If you try to derive if you have if you follow the solution to this equation, then you find that, say, a sound wave will not dissipate, will travel forever. Dissipation comes if you, but you know that dissipation should enter, and dissipation enters at the next level in expansion over length scale. In other words, the time for this dissipation to happen diverges as the length scale of the perturbation goes to infinity, and so forth.
So in other words, if I take, as you said, if I take Schwarzschild black hole or something, so I can never find out dual gauge theory with ideal description, because as you said, they reach thermal equilibrium instant very soon for compact small black holes. Or
for small black hole, you never have to think about hydrodynamics. You have to think about hydrodynamics only for the large black hole. And for the large black hole, there are the equation that describe thermalization is this hydrodynamic equations. What happened is that in order to see thermalization, you have to work to next to leading order in the hydrodynamic description.
Is it possible to have a gravity dual? So
Yeah.
I don't have any higher term. I have only ideal description. No other term.
No. I don't think you have. There is always some dissipation. The limit when you can neglect dissipation is the limit that you take. That means that, say, we are talking to each other using a sound wave. And that sound wave travel in a time that is proportional to the distance between us, right? Divided by the sound speed. The dissipation happened at a much longer time scale. So by taking the limit of low frequency, you separate two scales. The time scale for the long wave, for the sound wave to travel from one place to the other, and the time scale for it to dissipate. maybe I have some problem in the tutorial where you see this separation that happens between two time scale. So here, let's write down some. You can write down. You have to add here in order to see dissipation. You add here tau mu nu, and tau mu nu is constructed from u mu derivative and some and temperature. The derivative can act on temperature as well. Now there is a and it's tau mu nu has one derivative, and so this tau mu nu is much smaller than T mu nu ideal. Okay, because we are working in the limit when the derivative is small. However, if you look here, you see that that the separation between the ideal part and the non-ideal part is not unique. You can change slightly this u mu and then shuffle between the two terms, and or you can change slightly the temperature and then shuffle this T mu nu between here and here. Okay, so there is a slight. You can change u mu to u mu plus something delta u mu. Okay, and then that corresponds to tau mu nu going to tau mu nu minus epsilon plus b u mu delta u mu plus u mu delta u mu. Okay. In order to have to completely fix the separation between ideal part and the non-ideal part of hydrodynamics, we have to impose some condition on this tau mu nu. We need to impose the following conditions. So let's impose, and the same for t goes to t plus delta t. Okay. So we impose u mu tau mu nu equals 0. In other words, what we impose is the following. What we say here is that we would choose the definition of the rest frame of the fluid velocity, so that in the rest frame u mu equal 1, 0, tau 0, 0 equal tau 0 I equals 0. That means that the energy density and the momentum density is all in the ideal part, not in the dissipative part. Okay. It is, one can think about that as just a mathematical way to fix this indeterminacy in the separation between two parts, the ideal and the non-ideal part. And in the literature, sometimes this condition is called the Landau-Lifshitz frame. Now, with this choice of the frame, one can show that tau mu nu has to be proportional, has to be dependent only on two Lorentz, can contain only two Lorentz structure. Let me write it down here. So after this is done, tau mu nu has to be equal to the following. And the derivation of that you can find in Landau-Lifshitz. tau mu nu has to be equal to so there are two projection operator beta, where p mu alpha is nothing but g mu alpha plus u mu u alpha. So this projection operator makes sure that this tau mu nu is perpendicular to the velocity. Okay, so here I'm writing down what so, for example, one can think about terms like d mu, d nu t, for example, but they are completely eliminated by the imposition of this Landau-Lifshitz frame choice. So this term does not appear. The only Lorentz structure that appears are these written here, and the two coefficient here carries the name of shear viscosity. And this one is the bulk viscosity. Yes.
Can we understand this constraint as some choose of gauge, specific gauge?
It's not exactly a gauge. It is some reparameterization of variables between this tau and u mu. So there is some change of variables that leaves the physics unmodified. And that is the things that we fix here. So in some sense, it is a gauge. Yeah, in this sense, it is a gauge choice. Okay, so now I'm going to do the following. I'm going to use this equation to compute some correlation functions. We have said the following, that the hydrodynamics can be thought of as a low energy effective theory. As an effective theory, it has to have prediction, and the prediction should be valid in the regime of small momenta. It's a low energy effective theory which we can use to extract small correlation functions at small in the long wavelength limit or small momentum limit. So I'm going to try to compute or describe at least how to use this theory to compute correlation function of component of the stress energy tensor. Of course, in order to compute the full function, we need to know the full microscopic theory. Our goal is more modest here. We want to compute this correlation function when x minus y is much bigger than 1 over t. Yeah. 1 over the temperature.
So for these all calculations, that how can you they're all using boundary?
It's right now I'm talking about the quantum field theory on the boundary, and next lecture I will talk about how to use gravity dual to compute either the viscosity.
So metric G alpha beta is the exact
Boundary, yeah, is the boundary metric. Principle for simplicity, you can set that to flat.
flat.
Yeah, but right now I'm going to use the fact that I have this formulation of the theory in curve space in order to find out the correlation function. So there is a theory, there is a formula called the linear response theory. Which tell us the following. If we have a system with the Lagrangian L, and then we add into this Lagrangian perturbation j times phi, j is small, then the expectation value of phi is going to be related to the 2-point function j of y. So let me write it down first symbolically. Here, suppose, so yes, delta phi. The change of phi is going to be equal to the strength of the perturbations convoluted with the 2-point function. Okay? 2-point function of interacting theory. Yeah, so this is the operator in L. Okay. Have you seen, anybody seen this? People have seen that before. Roughly speaking, one can write down the path integral and then derive this. Here I'm doing a little bit of a shortcut because there is a subtlety at finite temperature on what kind of Green function we have to choose here. So here I'm just follow the physical argument that if you have a perturbation can influence the system only in the future, but cannot influence the system in the past. So this correlation function here has to be thought about as the retarded Green function. Defined as x minus y is equal to theta x naught minus y naught. X y. Okay. And actually, you can also derive this from path integral if you know how to formulate the path integral for quantum field theory in Minkowski space. It can be derived from the closed time path or Schwinger-Keldysh formulation of thermal field theory. Okay, so here I'm just appeal to physical intuition to motivate that this one has to be retarded Green function. Any question about this formula?
In this Green function with average under bottom of theory with gradually delta plus j phi, or just quadratic?
It's a good question. Actually, this formula is the first expansion over j. There is j square. Here we take j equals 0. Here, j equals 0 here. So it is the formula of linear response, linear in the strength of perturbation. Okay. So this one.
Is there any, can this linear response theory be generalized for non-thermal complete fields? I mean, is it necessary for this theory to be thermal?
No. It's not necessarily. On the other hand, if it is simple in the case of thermal field theory, because the correlation function, a thermal state is stationary and uniform over whole space. So the Green's function is a function of only the difference between x minus y. Otherwise, you would have to have correlation function that are function of x and y separately. I haven't thought carefully about that, but because I always think about this formula in the context of equilibrium, but I think it can, you can generalize it to a non-equilibrium state. But then this Green's function has to be a function of x and y separately. Okay, so how we are going to use hydrodynamics to compute correlation functions? Here we are going to do the following. We will think about this J as H alpha beta, the metric perturbation. Phi is T alpha beta. Okay. In order to compute two-point function of stress energy tensor, what we do is that we turn on metric perturbation and then find out the response of the system. And then that read out from that the correlation function. Basically, what we do is that we have a fluid, and then we imagine we have a source of gravitational field, gravitational wave. We pass the gravitational wave through the system and then watch the response. Okay. So how? Let's consider simplest perturbation. So we can have most general case where H alpha beta is non-zero, but I'm going to consider one particular case when there is only one component of the metric is non-zero. That is H xy, and let's assume that is much smaller than 1. So g mu nu is eta mu nu plus h mu nu. And I turn on only this perturbation of the component xy of the metric. Okay. Now, this hy, and there is no dependence on x. Everything is just a function of time. Now, the reason why I choose this case, it is because it is the simplest one. That is when the, if you think about classification over SO3, XYZ classification of the spatial SO3, this one is a tensor, belongs to a tensor part of the perturbation. It is a spin 2 gravitational perturbation. As a spin 2 perturbation, it cannot excite any variables in the hydrodynamic equations. Think about what can it excite. You can have excitation of temperature. T now can be T0 plus delta T. Now can be a function of time. But this delta T has to be 0 because temperature is a scalar, while we are exciting a tensor mode, and the tensor mode cannot into the linear level cannot excite the scalar mode. So T equal T0. How about U? U is equal, can be 1, and then can have plus O of V square, right? And then it can be V. But V is a vector. A vector cannot be excited by a tensor, so this one is also 0. So fluid cannot respond to this perturbation. On the other hand, if we look at the stress tensor, in particular, if we look at this component, Txy, okay, and you just follow this one, then there is one, the most relevant part will be this Vyy, and then minus eta delta x uy plus delta y ux plus etc. Okay. There are other terms, but believe me, they are not important. So this projection give you 1, so I will erase them. So just Txy is equal to this. Now, the important thing here is that these are covariant derivatives, so we have to be careful. It's equal to minus eta dx uy plus dy ux minus 2 gamma xy here, and then lambda u lambda. They are xx, pxx is equal gxx, right? So these are 1, basically 1. So if you follow all the math correctly, then they just drop out. So here we have in this last term, so this one is, of course, this one is 0. This one is 0 because the velocity of the fluid is equal 0 everywhere. The fluid doesn't respond to the flow, to the perturbation. But the last term is non-zero if lambda is equal 0. This is non-zero. So let me write it down up here. Equal to minus eta 2 eta gamma 0 xy u0. Okay, so from now on I will be not very careful with the sign. It can be plus or minus eta d naught h xy. If you compute the Christoffel symbol, this is equal to the time derivative of h xy. Okay, so we find that the stress tensor has a, there is a term in the stress energy tensor. I forget one term that is also important. There is gxy here. There is in the ideal fluid part, there is a p gxy that I add here. So there's minus p hxy. Yeah. The system response to the response of the system can be characterized by the 2-point functions. What we found here is that in this regime we have found the 2-point function to be equal to p minus I eta omega. So here I've written down this formula in momentum space. Q is equal 0 because we are considering perturbations that are uniform in space. It doesn't have any spatial dependence here. All this calculation can be redone. If there is a perturbation, we have to think very hard how this velocity and the temperature of the system would change. In this simplest case, we find the 2-point function of this component of the stress energy tensor to be equal to pressure minus I eta omega. Okay.
So your argument was that because hx was a tensor under SOP, we cannot excite scalar like t or vector like u.
Mm-hmm.
But if I make a hxy function of x,
If I
make hxy
Mhm.
function of
X.
x, so it is not a then okay.
then you can excite things. Yeah, there is. I hope to have one problem in the tutorial where that happens. Yeah, when you can excite some fluctuation of the space, and then you will have a more complicated 2-point function. Here, the 2-point function has a real part and imaginary part. What we have done here basically is to derive the so-called Kubo's formula. So this is the last formula that I will write down in this talk. This lecture. basically we have the Kubo. Tell us eta is equal imaginary part of the retarded Green function of the xy component of the metric equals 0. Okay, so here we have established the the formula that relate the shear viscosity of a fluid with the correlation function. And in the next section we will use ADS-CFT correspondence to compute this correlation function and find out the value of the shear viscosity in n equal 4 super Young mills at large stove coupling. Any question?
What happened to the last term there? The Gxy also?
Which term? Oh, the bulk viscosity term. It contains d dot u, so d dot u is equal 0. Yeah, it's covariant derivatives. It's a scalar. Basically, it's a scalar. So a scalar you cannot write down something proportional to hxy. So in order to find the bulk viscosity, you have to turn on some more a scalar perturbation of the metric. And then you can write down a formula. There is a similar formula for the bulk viscosity where you have G II JJ, the retarded Green function of the trace of the spatial part of the stress tensor. Yeah. There is a similar formula for the bulk viscosity that we can also derive.